This is Chapter 5, Igneous Environments, Lecture 1. Our goals for this chapter include to explore how magma forms, moves, and solidifies. We'll also look at the characteristics and origin of igneous rocks, including different settings of melting and how to recognize igneous rocks in different landscapes. Starting off, we're looking at igneous environments in northern New Mexico. All right, so let's look at the features of this landscape. This is around the PHYS caldera. It's a circular depression with hills inside of it. All right, it has light colored ash in it as well. Here's kind of a landscape view. The green areas in this diagram are the high points. The Rio Grande River is to the right. I have it here. We have a lower valley surrounded by high mountains on either side. There are smaller volcanoes and dark lava flows also represented here. And then we have an area with huge crystals and igneous rocks. This is the Harding pegmatite. And some of the crystals at this pegmatite mine are more than 2 meters long. So between this caldera area with huge crystals and area with smaller volcanoes, we have different igneous features and what controls the type of igneous feature that forms at each location. All right. So these are all rocks that formed from molten material, but what makes a difference here is the rate at which they cooled and whether it was underground or extruded above ground. So that's really the big part of this chapter. These are all different igneous rocks with different textures. So in the upper left, we have very large crystals with a sharp V for scale. Within the Black Hills of South Dakota, here we have, that's a pegmatite by the way, coarse-grained igneous rock. Still pretty large crystals. Medium-grained igneous rock. And then a fine-grained or fine crystalline igneous rock. Okay, here's some other igneous rock textures. This one is glassy. This is what we call porphyritic. It's when you have crystals within a very fine-grained matrix. So glassy, porphyritic. Vesicular, it's fine-grained igneous material with holes inside. And then welded. That occurs when particles of pumice and volcanic ash are flattened by overlying ash. That happens when rocks are still hot, mostly not molten. But volcanic ash rocks aren't always welded. It's just something that can happen. Okay, so this is a diagram of a volcano. We're going to see different igneous rocks resulting from a volcanic eruption. It's not all going to be the same thing oftentimes. So you have this column of ash, and that ash cools before accumulating on the surface of the earth, so it might not be forming a welded rock. It can also result in a pyroclastic flow. It's really hot and destructive, and you might see welded textures resulting from that flow. You can have an eruption of lava that can form something called volcanic breccia. You can have rapid cooling. Rapid cooling can form a lot of different things, but volcanic glass is one of them. Slower cooling further down would result in a coarse-grained igneous rock, so with large crystals. If you have slow cooling followed by fast cooling of material, you can get porphyritic texture. So slow cooling would result in large crystals, and then fast cooling would be like the fine grained matrix that you see in a porphyritic rock. If you have water added to magma, you get these incredible larger crystals to form things like pegmatites. Okay, so non-welded perhaps versus welded. Glassy vesicular material can come out of eruptions. You get fine-grained igneous rocks from rapid cooling if they're beneath the surface. Expect these at the surface, glassy or vesicular textures. And then slow cooling at depth would be larger crystals. So the pattern that we're seeing here is the slower you cool, the larger your crystals, and slow cooling occurs underneath the Earth's surface. Okay. So these are all different types of igneous rocks. To classify them, we can say look at color. That's one thing, but also really useful is to look at different sizes of crystals. And say these are like fine grained. These are larger crystals. So perhaps these formed from fast cooling. This one looks almost porphyritic. I can see these crystals within a fine matrix. So perhaps there was slow cooling at first and then fast cooling. And these larger crystals probably formed through slower cooling underneath the Earth's surface. These were extruded. Okay. There's different types of igneous rocks classified by their composition, and color can be very reliable for that with igneous rocks. Composition equals mineral content, and then also grain size is another thing we look at. So these are essentially the same mineral composition, but one is coarse grained and one is fine grained. And these are felsic rocks. They are generally light in color. The granite forms slower than the rhyolite. Granite is intrusive, formed underneath the Earth's surface. It has some darker minerals as well. This is extrusive, formed at the Earth's surface. You can also have an intermediate rock, igneous rock, and that's got mostly dark and light minerals, kind of 50-50. Diorite is a good example. It's an intrusive igneous rock. Okay. Light minerals in the igneous sense are felsic minerals. Dark minerals are considered to be mafic minerals. So the intermediate has equal parts generally felsic and mafic minerals. With andesite, that would be the extrusive version of diorite. Also an intermediate between a felsic and a mafic igneous rock. So getting into mafic rocks, those are mostly dark minerals. Gabbro would be your intrusive example. It's coarsely crystalline. Basalt is extrusive. It's going to be dark minerals that are finely crystalline. In this case, there are vesicles, little holes. That's where gas is escaped with rapid cooling of that material. You can go further into ultramafic rocks like peridotite. That is an intrusive, coarsely crystalline ultramafic rock. The upper mantle is composed of this. You can also have ultramafic lava, extrusive material. This is finely crystalline with unusually long crystals. Okay, so classification of igneous rocks can look like this. Okay, so in color, you have lighter versus darker, felsic to ultramafic. So coarse-grained felsic igneous rock could be a granite or a pegmatite. A fine-grained felsic igneous rock could be rhyolite. You can have other felsic rock types that include obsidian, pumice, or tuff. And there's some overlap into intermediate here as well. That's what these lines show us. And the minerals that overlap with like felsic are quartz, potassium feldspar, and biotite, and plagioclase feldspar. But that's also present in intermediate and mafic, and maybe a little more calcium rich as you go from mafic to ultra mafic. We don't expect to see much pyroxene in a felsic igneous rock, nor would you see olivine. That's kind of limited to mafic and ultramafic igneous rocks. Okay. So to kind of change the pace here, we can look at this image and identify 4 ways in which energy is transferred from one place or object to another. Okay. So one way could be conduction, where energy is transferred via direct contact between the stove, which is hot, and a cooler object, which is the pot of water. You can have radiation, where energy is transferred by electromagnetic fields just to the air here. You can have convection, which is a vertical heat transfer by flow of a material. You see a convection cell where the hot water rises, cools, and then falls back down, heats back up, and goes up again in a somewhat circular path. Also, energy can transfer by moving a mass and its contained energy. So the water's hot and we move it elsewhere. It's not really used much in the book. You can think about this for your discussion this week about each type of energy and how they might be transferred in other parts of nature. All right, let's talk about melting rocks, because we get these igneous rocks from molten material. So first you have a solid material. Pressure tends to hold that mineral lattice together, but we increase temperature, introduce heat, and that vibrates atoms and it breaks bonds, and suddenly that mineral lattice or rock is now a liquid. So how could a change in temperature or pressure cause melting? Well, we can represent that with these pretty simple diagrams. We have pressure increasing on this axis and temperature increasing on this axis. So from low to high, low to high. The line slopes down to the right because higher temperatures are needed to melt a rock under higher pressure. So all of this area is representing a solid rock, like points A and C are solid. Point D is the transition between liquid and solid, and B is a liquid rock. The position of the line depends on the composition of the source rock. Okay, so point B is the same pressure as point A, but there's a higher temperature present at point B, so point B is a liquid. It's just hotter, you know. Point C is at the same temperature as B, but it's at a higher pressure, so it plots in a solid field. And then point D is going to have both solid rock and magma present. All right. So how could changing conditions cause a rock starting at point A to melt? Really just add heat. All right. How could changing conditions cause a rock starting at point C to melt? You could add heat. You could also drop the pressure and have temperature remain the same, and suddenly it is also a liquid. Okay. So when a rock at point A is heated with or without an increase in pressure, it's melted. as in what's happening at point B. Point A to C shows that if the temperature increases but pressure is sufficiently high, the rock still is not going to melt. Okay. So what happens when a hot rock, this is hot, at point C is uplifted so rapidly it doesn't have time to cool off? Okay, so temperature remains the same, but we drop the pressure drastically. We go to point B and suddenly it's a liquid. We call this decompression melting. For that to occur, the rock must be really hot and lifted up to the Earth's surface faster than it can cool off, and it'll melt. All right. Something also happens if you add water to a rock. Adding water lowers the melting temperature of rocks. So water can lower by as much as 500 degrees centigrade or Celsius the temperature at which a rock can melt. So what happens to a rock at point E if a small amount of water is added? It's quite hot and dry, okay? So what can happen is that it'll melt. So it was a solid, we added water, and we're actually moving the boundary for liquid rock here, and suddenly point E is a liquid as well. It melts with the addition of water. All right, and we will stop there for today and pick up with more on the formation of igneous rocks.